Okay, the door is closed, so I guess I should start. That's the the sign. Thank you so much for coming. This is my first tech talk at any conference, so I really appreciate the opportunity to speak. And I'm really pleased that anybody turned up. And it's great to see some of you here that I know really know C++ better than me. So I hope you'll be kind, and I hope you'll actually enjoy this presentation. I'm going to talk a little bit about the practical challenges of building a memory profiler for a production piece of software. So first of all, just a show of hands, who enjoys finding memory leaks or searching for memory leaks? Enjoy it. Good challenge, right? Okay, maybe this talk isn't for you. This is mainly a talk for people who don't enjoy finding memory leaks. Who's ever been surprised where a memory leak or abnormal memory usage turns out to be? Right? I think that's really the core of this talk is going to be, how your code can tell you things that you don't expect, if that makes sense. So, a little bit about me. I'm one of those people that Bjarne referred to as those kind of hardware hackers who think they're programmer types. But I've been trying to do better than that and actually learn C++ over the years. So I actually spent 15 years in kind of electronic music sequences, games, high-performance computing startup. Anybody remember Occam? Parallel language from many, many years ago. So kind of dealing with firmware and device drivers and parallel systems, and that passion for really understanding how the machine works has really kept with me through those years, and then 20+ years actually at Bloomberg, doing primarily high-performance C++, graphics, and now quite a lot of integration with JavaScript, dynamic environments layered on top of C++. I'm a developer still. I'm very proud of the fact I still know how to actually run the compiler. I'm a manager and a mentor in working in our London, New York, and San Francisco offices, but based in London. And I'm really passionate about STEM and STEAM with the arts in there, because I still think that creative thing is important, and diversity and philanthropy at Bloomberg. So who's Bloomberg? Forgive me for just spending 1 minute telling you who Bloomberg is, because I think it's a relatively unfamiliar company to many people. Born 1981 as the first real electronic bond calculation system for trading floors. After Mike Bloomberg left Solomon Brothers, and really we were kind of one of the first tech startups back in the 80s. Nowadays, the Bloomberg Professional Service, presented through a thing called the Terminal, which is basically a real-time browser, soft real-time, evolved into a desktop system that now is used by over 300,000 traders and researchers on the trading floors around the world, providing data analysis, communication, and trading tools. And also, the real-time data is available in enterprise products as feeds, 100 billion updates a day, sometimes 10 million updates per second. An update can be a change in the price, it can be a news headline, those kind of things being delivered. We actually have our own news and media departments, generating 5,000 news stories per day in 120 countries. 19,000 employees, over 5,000 of those are software engineers. So software engineering is a really important thing at Bloomberg. It's not just something that we kind of have to do to get by. Software engineering really forms the core. So tech at Bloomberg, as I say, tech company often people have never heard of. We have 900 developers in London out of the 5,000 total. Originally, we were very much a Fortran and C shop, kind of running often on custom hardware with custom context swapping OSs. We were a very early adopter of server-side JavaScript back in 2003. And if you think that Node wasn't actually really born in 2000 to 2009, so we're quite proud of that. Something we're even more proud of is our presence on the C++ Standards Committee for over 10 years now. We've some of you here will know our friends, John and Alistair and so on. And that involvement has really, really helped us. Something that we've been pushing for a long time and is now part of C++ 17 is this concept of runtime polymorphic allocators, the PMR namespace, which is something that we use internally. I'll show you a little bit of that later on. But it's really helped us to kind of get, everybody talks about C performance out of nicely structured C++, but that's the kind of thing we've been aiming for for a while, and we contribute to open source initiatives. We do have a public presence on GitHub, which you're welcome to have a look at, including our reference SDL implementation that is there. And we also have presence on the JavaScript TC39 committee and have been sponsoring and helping define and develop CSS grid layout, async await, big int, and now private data types, which are coming soon to JavaScript. So feel free to look at our tech blog. There's a few things on there. I really hope that some of the code in this talk I'll be able to open source soon. Apologies that it's not there yet, but I really hope we're going to be able to do that. So the Bloomberg Terminal, this is the thing, this is my passion, the thing that my group is very heavily involved in developing. Originally it was totally homegrown terminal on the desktop with a very custom UI stack. And my friend Alex, who's here, has spent the last 10 years trying to delete most of my code that does that. And he's pretty good at that, actually. It's now, we've now evolved that, and a lot of the core kind of UI framework within it is actually built around open source Chromium, WebKit, Blink now, I guess, which gives us HTML5, CSS3, standards compliance internally, access to this state-of-the-art V8 JavaScript engine, and we get for free things that Chromium core is doing, like hardware accelerated graphics, accessibility integration, so the whole hookup on the desktop, certainly under Windows, to the accessibility framework. We have a couple of traders I know of who actually are completely blind, who managed to actually trade successfully with the screen switched off, which I think is amazing. Fantastic to see how a system like this, which is so UI heavy, can actually be used by somebody who has those challenges. We add to this kind of Chromium core a custom real-time data processing pipeline called Data Layer, which allows our application teams to build and model sophisticated sort of data transformation, from the incoming stream into the UI. You may have a 100,000 row trading blotter, which is dynamically updating and needs to be sorted live and filtered live. The user obviously is only looking at maybe 40, 50 rows on the screen, but you need to be doing that processing real time in a way that is flexible. So it's you can kind of think of it like an Excel-like and a streaming SQL-like queries into the UI. And we kind of add on the top of that true push in order to leverage our multicast data fan out that we have across the world. And we do other things like integrate with biometric authentication devices so that when you log in, we know it's really you, which is quite important if you're a trader. We really care about performance at the desktop. It's really important that we have low latency in terms of data coming in to actually data getting on the screen. Scalability, we're displaying maybe hundreds of real-time components on the desktop across maybe up to 8 high-definition monitors, all from one PC. Mainly 2D graphics. Graphics cards nowadays are fantastic at 3D graphics. You still have to work quite hard to get high-performance 2D graphics, actually, for mainly text and charts and so on. Reliability, crashing or freezing when the markets are high volatility is a disaster. We really must be writing reliable code. It's not a rocket, it's not a car, but as far as the traders are concerned, they really want this to stay working. And profiling us really helps, obviously, to target these hotspots for improvement. CPU profiling, obviously, but also memory profiling. If you've got a system that needs to run for a long time, you really need to understand how memory is being used in that system. So this talk is very much focused on how you kind of apply CPU profiling principles to memory, and doing that actually within the application itself rather than using external tools. And we're doing this because this thing has to work every day here. This is the New York Stock Exchange floor, and this is the kind of environment where this front end to this a wealth of data needs to actually run all day. So memory leaks in 2018, really? Surely memory leaks are a thing of the past. RAll, everybody's writing clean code, yeah? Obviously not. Right? We have to deal with code that we're not writing today. We have to deal with legacy code, third-party code, open source code, old libraries we've brought in. And even then, non-leaky code can feel like it's leaking. If you find, if pools, for example, are being used in an unexpected way, they can use a lot more memory than you think they might be using. So, and that can be sometimes hard to spot these kind of patterns. In addition, which is something that's very relevant for us, is mixed environments that combine managed languages like JavaScript on top of native C++, where you've basically got proxy objects that connect your JavaScript to native objects. You get complex and non-obvious life cycles for your native objects. You're at the whim of the garbage collector unless you're very, very careful. So you can find that your native C++ objects can live a lot longer than you might want them to or expect them to. So I'm going to just give you a very, very quick case study here. So here's one of our components on the screen. It's called the GD, or graphics display, or something really imaginative. The very simple component, just bits of text and numbers and some charts. I was looking at a memory issue with this, and I was finding that basically this code, which just pulls in some data from some kind of source, probably the network, parses that data and builds a world, builds that representation on the screen. When it was working fine, it was using 500 megabytes of memory. It was quite a big world. However, if amongst those input packets were some errors that would get sent to some error stream, if they were present, then the memory usage of this component would jump to 800 megabytes consistently. I was thinking, why? Must be surely something in this parse line function is, partially handling, a message, and, it's building some state, and then maybe it's leaking, or it's, I don't really know. How am I going to find out where this memory is going to be used? So we're going to come back to this example later, but this is the kind of the crux of why we were doing this work. So the usual strategies for finding memory issues: looking at the code, of course, deleting, disabling code till the problem goes away, adding logging everywhere, trial and error, hunches, sleeping on it, not sleeping sometimes, custom allocators, you can put in there. C++ is obviously very flexible for custom allocators, but you can't always plug them in everywhere, particularly when you're dealing with somebody else's code. A CI system that runs code tests with test allocators installed. Fantastic if you can build those tests in, but again, it's not always appropriate. Profiling calls to malloc, actually just using a standard CPU profiler and see, well, who's calling malloc? Sometimes that can give you a clue. External memory analysis tools, I started doing this work before some of the latest compilers and tools were released, which actually do solve some of these problems a little bit, but in a different way. Intel vTune has a pretty decent memory profiler built in. Visual Studio 2017 now hooks into event tracing for Windows, which is the kind of kernel level logging that Windows has, and that can record memory accesses. I would argue that what I'm going to show you actually gives you a little bit more context than some of those tools, and maybe, certainly in some cases, is more useful. So what we're trying to do when we're trying to fix a memory issue is we are trying to find out, we're trying to answer this question: which code paths result in the most memory usage, and how does that change over time? It really is a classic profiling problem just concerning memory. As I say, some modern IDEs and debugger tools can help, but if your code can tell you, it can also add extra context that tells you more about that memory. So how do you build a memory profiler? As we say, the call stack defines each unique code path all the way down to malloc. So what could we do? We could intercept malloc and free and realloc and calloc and so on. We could figure out where we are, look at the call stack at that point. We could build a histogram of unique call stacks to allocation total at that call stack. So for every unique call stack, we can just keep a sum of, well, actually how much memory has been allocated by that unique call stack. And then we need a way of visualizing the result to make sense of this data. And we need to do this quickly. We really don't want our application to slow down too much when we have this mode enabled. Maybe a little bit of a slowdown is fine, but no more than a few percent perhaps. So how do we intercept malloc? On Windows, our application primarily runs on the Windows desktop, so sorry about that for you people using Linux, but the principles are very much the same. So on Windows, the C runtime library is actually just a thin wrapper as far as heap is concerned around functions that are actually in kernel32.dll. So malloc is like 4 or 5 lines of code. It basically just calls into heap alloc in the lower level. Same for free, realloc, calloc. Calloc just adds the kind of the zeroing out of the memory. msize gets you the size of any object. So pretty easy to understand how this all fits together. So what you can do, and this we actually borrowed a trick from older versions of Chromium, which we found conveniently when we started to embed Chromium in our terminal, was that old versions of Chromium, what they were doing were actually modifying the standard C runtime library on Windows and removing malloc, free, realloc, and calloc, and msize from that library, and then replacing them with custom versions on the link path that would be used instead. And because the original malloc free and so on were very, very thin wrappers onto heap alloc and heap realloc and heap free down in kernel 32, this is a very easy and safe thing to do. So you can see here the commands. There's actually a bit of Python in the Chromium's code base that actually does this to actually pull these, generate a new version of the library that actually pulls these object files out of that library for you. I think on Linux you can just, it's an order of precedence, right, for linking with symbols, whereas on Windows, as soon as you've got more than one reference, it will fail. You have to actually, you can only have one version of malloc on the Windows link line. So how do you actually do that? So this is the replacement malloc, for example. So the replacement malloc does a heap alloc. It actually calls heap size to actually find out what we really got. If we ask for 3 bytes, we're probably going to get 4 or maybe 8. So it's actually worth knowing what you actually got. Of course, the definition of what heap size does changes, and sometimes it will give you what you ask for, and sometimes it will give you back actually what it allocated. This seems to be the best way of handling that. Very easy, we can just keep track. In this callback, how much memory we allocated in total. And then we're going to call back to some instrumentation that we've installed, a callback. To set this up, we actually need to initialize a static variable, which gets us the process heap, which is the main heap that any application will use on Windows. And there are some flags you have to set. This is basically copied from the C runtime in order to make sure that is set up correctly. Nowadays, there's this thing called the low fragmentation heap, which is used by default on Windows. But this all sort of smells a bit nasty, right? You don't really want to be hacking the C runtime library. And also, it only works if you have the ability to recompile and link everything that you want to instrument. It's not great. So maybe there's a better way. Strategy 2, actually intercept what happens at load time. So if we have the same structure. We have the C runtime library calling into kernel 32. But the loader, when your application loads, is going to resolve those references into kernel 32. And if you actually look at how this works, it's pretty easy to actually intercept at runtime. So if you look down on the bottom left of that box, that's my call from malloc to heap alloc. What actually happens is the call calls to another piece in the same code section that actually has an indirect jump in it. And that indirect jump, you can see, actually jumps via a piece of memory in the data section, which is writable. And that actually points to the address of the loaded heap alloc method in kernel32.dll. So if I change that address, that yellow one, the 0x77879426, I can actually have all calls to heap alloc from that C runtime library instance call into my code. Sounds a bit messy, right? It's all described very, very clearly in this document from 1994. Nothing much has changed in over 20 years. So you can do that. Conveniently, Chromium, hooray, actually has a little helper class that does this for you. IoT package function actually does this for you. Every time you call it, you can replace all calls from imported module to function name in so-and-so module with calls to your own new function. Fantastic. So how do you use that? From some DLL that's not part of the main or another DLL you want to instrument, you just instantiate these objects and set them up to basically patch in your own functions to intercept these heap allocs, heap frees, heap reallocs. So here's the intercept for heap alloc. It calls the real one, which in this DLL is not patched, so it actually calls through to the real one. And then we're going to just add some instrumentation in our record allocation internal here. Likewise, for free, we're going to call the real heap free. We're actually going to find out what size it was first, and then free it, and then call into our own deallocation instrumentation function Heap realloc kind of has to do two things. It has to remember what the old size was, do the realloc, do the new size, kind of decrement your total count by the old size and add in the new size, and also record a deallocation and an allocation, which is likely to happen in the case of realloc. That's it. So we now have successfully intercepted these heap functions without actually changing any code, which is a nice place to be in. So the next stage is to figure out where we are. How do we get the call stack? Conveniently, both on Windows and Linux, there are system functions that do this for you. On Windows, it's capture stack backtrace. Linux has backtrace and backtrace symbols to resolve what you get. Conveniently, the Windows one, and I don't know why they did this. Maybe they were thinking of me when they designed Windows. They actually give you a hash, a unique hash for that unique call stack as part of the traceback, which is fantastic because now we have a key for looking things up, a key that defines every individual unique call stack. On Linux, you have to make some kind of hash, but I'm sure everybody in this room is capable of writing a hash function or using a hash function. So this is just the code that would actually, based on that, will allow you to basically build a vector of return addresses from the stack and store that in a just in a map that allows you, for any of these hashes, to actually go back eventually to the real call stack. And then also have a separate map you can use to actually resolve the symbols for each of those addresses in that vector, if that makes sense. So this is just a way of being able to, in any of those intercepts, in fact, we only need to intercept the actual ones that do allocation, the malloc and the realloc, to record where we are. So now, what are we going to do? Now we know where we are, we have this intercept that's happened. We're going to build some kind of histogram. So in this malloc intercept, we're going to figure out where we are from the call stack and the hash, and we're going to accumulate the size per unique call stack in another map, simply that has an accumulating counter per unique call stack hash. Very, very simple. In addition, we want to remember for that particular malloc address we got back, where did it come from? So we're going to have another table that maps malloc pointer back to some descriptor that tells us the call stack of where the malloc came from, so that we can find it, so that when we call free, we can use that address that was given to free, look up where we came from, and then decrement the size that we're storing for that particular unique call stack, without having the program need to carry any extra state. And we need to do this quickly. So these are what our data structures look like. Pretty simple. We have this descriptor for a malloc, which tells us the size of the malloc and the unique call stack it was actually called from. We have this collection called address map type of current live mallocs looked up by the allocation pointer. We have this other map, which is per unique call stack, accumulating size of memory allocated, and that's memory map here. We have each traceback represented as a vector of return pointers, and then we store those in another map, which is keyed by hash to tell us from any hash how do we get back to the actual call stack in order to actually display some kind of meaningful answer. And we also have a final map, which is probably going to be filled in by some other thread that actually goes and resolves all the symbols that we have in each of these call stacks. This is how we'd actually do it. So within the actual intercept, we would build the walkback. We would build one of the descriptors. We'd put it in the address map, and then remember and accumulate for that particular call stack how much extra memory we're adding. Either accumulate or add a new entry if this is the first time we've seen this new call stack. Similar principle for free. We don't actually need the call stack anymore because we just look up based on the free pointer where the call stack was that allocated us, and therefore we can decrement the memory that was used by that particular malloc. One gotcha. Our little data structures here, which we're using to store this, are going to use malloc because they are they're dynamic objects, they're maps, right? So we're already inside malloc, so we want to be a bit careful here. So even in a single thread, we need to have some kind of protection. So here's the most basic protection we can have within a single thread is some simple variable that tells us whether we're already in malloc already when this happens. Not a very nice way of doing it, right? So can we do better? Of course, we can do better with a little guard that keeps track of that. Still not the full solution because our internal data structures are shared amongst multiple threads, so we do need to have some kind of locking around our internal data structures when we are actually doing this instrumentation. But in addition, this isn't, our static inner allocation Boolean really doesn't cut it in a multi-threaded environment. What we need to know is for any thread, is that thread inside malloc at the moment? Simple solution, actually use thread local storage for that. So that now per thread, we know whether we're already inside malloc or whether this is just a standard call to malloc that we're not right in the middle of instrumenting at the time. I was quite pleased to find this because how often do you actually find valid uses for thread local storage? This is one of them, I think. So I was quite happy about that. So how does this actually work? Very, very simple function. Let's see how the data structures update. So we call the first malloc. The address map gets in the description of our particular malloc. So we got address A, and it was size 10, and it had a particular hash. We also remember the total size of that particular callstack hash, and we start to build our kind of set of callstacks as we go. And we just follow this through. We add a new entry. Then we jump into another function. It's just another malloc, but it actually is now a different unique callstack. So we add a new entry in the memory map, and we also add a new entry in the traceback map as well. And we've now got a new symbol to resolve later, which we'll eventually resolve, which gives us all the data to produce some nice sort of output. And the kind of output we can produce is like this. So I ran an example, and it gave me this as the highest callstack that used memory. In this particular example, it was some heavy worksheet component, which actually was, from this particular callstack going all the way up, was using 300 megabytes of memory. Not a great way of actually looking at the data. So maybe we need more visual representations of the data. How about if we put this data in a tree? We now have this histogram where every histogram node can be kind of resolved to a vector of traceback addresses that within each individual callstack. So why don't we actually traverse those and build a tree representation that tells us the amount of memory used by individual return pointers in total. So I won't go through this in detail, but basically we just go through our histogram and we just traverse it and build up a tree, which then ends up looking like this. So you can see everybody calls malloc, and these are based by tree. These are the three biggest callers to malloc. The first one is some fancy tagged allocator that we have already somewhere in our code, and part of our code is using that. You see the stat context tagged allocator store at the top there. Further down, we have some just generic C++, which is calling our default allocator, which in our case was this thing called infrequent delete block list allocate. And you can see there's some code, probably some pool stuff that's actually using that. But also, there's something right down the bottom that is actually directly calling malloc. It's maybe not even C++ code, it may be C code. That's actually not using any of this stuff at all. So I think that's a step forward in how we actually instrument memory. But how about if we actually tried to show this graphically? Wouldn't that be nicer? So using this exact mechanism, but just building a tree traversal UI on the front of it, what can we do? So here's a piece of code. Nobody writes code like this anymore, right? Nobody calls malloc directly. Who knows? Very, very simple piece of code that allocates some memory and then waits and then frees it. What actually happens? There we go. So you can see that. That's actually showing the call stack that's allocated the most memory, waited 5 seconds, went away. Too quick, maybe? Let's just leak. And then you can kind of see this for real. So you can see we've actually got 2 unique call stacks here. One of which is the actual leak, obviously. The other one is actually the little vector we're building. If I hover over this, you'd actually see what they were, that we're actually using to keep track of the pointers. So immediately, this is showing you, and obviously this is a very simple example, what call stacks in my code are using most memory. Let's make it a little bit more, a little bit richer. So this is 3 little tests, again, that just show you the different call stacks that eventually call into malloc, but the proportion of each of those that is responsible for the 569 megabytes of heap that we've actually used here. Now, let's go back to our case study. So remember our case study was something that took in a load of data, input data, maybe it's JSON or some other format, and built a world from it. And what we discovered is when it ran perfectly, it used 500 megabytes of memory. When it ran with some errors and spat those errors out to the error stream, it used 800 megabytes of memory. So I ran this through the profiler. What happened? This is the normal case. What we'd expect. So we see about 500 megabytes of memory called from the places we expect it. That's the world that we're building. Fantastic. How about in the error case? What happens? So all of a sudden, we're using 800 megabytes of memory, which we know is the problem. We can see our world on the left here is the 500 megabytes, but look on the right. Look at this call stack. It's the operator input, right? Output. It's something to do with the logger. Why would the logger be using 300 megabytes of memory? It's one of these surprising cases, right? This was real. We actually found this. So let's go back. Well, what does a logger look like? So a logger is typically some kind of thread-based producer-consumer. You typically have another thread that's going to be writing to disk or to network that doesn't interact with some kind of queue in the middle that doesn't interrupt your actual program flow. What would that look like? If you just ran a simple producer-consumer logger, you get this. Well-behaved. Of course, if you're producing data faster than you can consume it, then it's going to build up memory, but then it's going to go away, as you'd expect. However, maybe you're going to be clever, and within your logging, you're going to introduce some kind of pooling. Let's just have a very simple free list here. So you imagine that the queue between the producer and the consumer is some list of strings, for example. But also, we're going to pool those strings so that we don't give them back. Rather than give them back, we're going to put them in a free list when they're finished with. What happens? This is, again, the standard producer-consumer with a pool. Of course, the strings end up building up in that pool. But you think, well, the string object itself is not very big. But you look a little deeper and you find out, well, there's nothing that's actually removing the string data from those strings before putting them back in the pool. So what happens if now and again I suddenly send a huge log message, which maybe is the source of the problem in the first place? What's going to happen is this producer-consumer is going to end up hanging on to huge log messages in its pool that it no longer needs. It's written them out to disk or it's written them out to network, but they're stuck in these pools. So let's be cleverer. Let's clear the strings before we put them back in the pool. So they're just basic empty string objects. Often doesn't help. What clear does to the string storage is implementation defined. Often it won't bother to clear out the memory that's been allocated for that string. Even resize 0 doesn't necessarily change the capacity of that string. It might. You just don't know. In our case, it didn't. What we found actually is the only way to really clear out a string before putting it back in the pool is to swap in an empty string. But then you think, well, what's the point of pooling if you're just swapping in an empty string? Well, maybe you do this for sizes that are bigger than a particular limit. So you get the benefit of pooling lots of small objects, but without the expense of accidentally pooling very, very large objects. And you do this, sure enough, what happens is memory usage builds up, and then as the consumer thread flushes out, the pool is well behaved. It still ends up pooling a little bit. You can see on the right here, lots and lots of tiny string objects, but you're left with the basic memory usage of your application is just the world that you expect it to be. So we've saved 300 megabytes just by understanding that actually memory usage was in a very unusual place. So I said earlier that there are some great tools, external tools, that could help you with some of this work. But The disadvantage of an external tool is that it doesn't really know the context of what's running inside your program. It has no idea whether, for example, the memory that's been allocated is for some kind of pool or some other use, or maybe it's a string type, or it's just memory. The point of running this kind of thing inside your application is you can extend these APIs to actually add context. So, for example, simply, we could add the ability, whenever we do an allocation from within a pool, we actually tag that and say, well, actually, within this thread, I'm going to have a little guard that just sets a piece of context in my instrumentation system to tell me that this is actually pool memory that's being allocated. Very, very simple. We just add these guards in when we allocate and deallocate so that the instrumentation knows that actually the thing that's going on is to do with the pool. And the way we actually implement this, again, is another piece of thread local storage, because this could be running in multiple threads, obviously, but within a single thread, we can maintain that context. And we just have another map, maybe, that just keeps track of, actually, this is an allocation that not only is using the heap, but is actually can be tagged as heap that is used by a pool. And what happens if we add that into the UI? Maybe we just decide to color it. So now we see this tree that tells us not only the code that's using the most memory, but how much of that code, how much of the memory that's used is actually designated as pool memory. Can be useful, right? You could obviously take this much, much further, add in lots more context that tells you about your system. Something that I'm working on at the moment is to make this kind of pool representation smarter. What you really want to know is, if I have a pool, how much of the data in that pool is kind of been lent out to the thing that's using that pool, and how much is actually held currently by the pool, to give you an idea of whether that pool is being used efficiently. We can actually do this using a kind of series of stacked allocators. Now, this is using the kind of Bloomberg BD style because that's what we use internally. Forgive me, you could absolutely replace this with the standard PMR memory resource that's into C++ 17. By just stacking these allocators, we have basically the allocator I just talked about before, which is a kind of a counting allocator with a guard that allows the instrumentation to know that we're in a pool, given to a standard multi-pool allocator, and then that given to another counting allocator, which is given to the application. So now if we actually look at the difference between the kind of top and the bottom counting allocator, that will tell us actually how much memory is held in the pool, currently ready for use, but not actually handed out to the application. So the intention is that we can start to add that into the instrumentation so that when we look at our tree view of our code, it'll actually tell us not only the callstacks, not only which data is pool data, but actually how much of that data is held by a pool rather than actually in active use by an application. Because you can, particularly we found if you use a pool at startup, you end up starting up things very, very fast because your pool's working well, and then you forget that this data is held in this pool forever. And once you go into steady state, that maybe that data that data was only used by the parser, for example, as you start up. But you don't need it anymore. So maybe you need to change the life cycle of that particular pool. Now, I just want to very quickly touch on mixed mode systems. As I mentioned before, we run an environment, particularly now we have Chromium embedded, where the glue that holds our desktop system together is written in JavaScript, and then that manages lower level soft real-time C++ subsystems. What we're finding, particularly with the modern ways people are writing JavaScript, for example, React style coding, where a single change to some state results in the whole JavaScript world being rebuilt. If that JavaScript is using some proxy objects to hang on to C++ objects, you can end up with your C++ memory footprint holding multiple invocations of the system. Because you're at the mercy of the JavaScript garbage collector. You don't know, the garbage collector doesn't really know the cost of each of these native objects that maybe it's referencing from JavaScript. And we found systems, somebody changes their their trading system buy ticket to a sell ticket. And that, just a simple change of that button for a React-style piece of JavaScript can result in a whole data transformation pipeline being created for the sell mode as opposed to the buy mode, but the buy mode still exists in memory. So what we found is that if you can't deterministically control how the garbage collector is working, and everybody says don't play with the garbage collector, you need to let it do its thing. Something we've done is actually adopted the approach that C# takes, another managed language obviously, the dispose pattern, where you can deterministically say, although I don't know how long my JavaScript object is going to exist for, I do know when I'm finished with the thing it references. So I'll implement in my proxy object a dispose method that allows me to call into the C++ and actually let that thing be destroyed. We found that to be very, very helpful for large native objects, such as our data transformation pipeline that we're using. And this is just an example of how that looks in ES6 style JavaScript. So that's it. I think I've kind of done it in the right sort of time, which has impressed me anyway. There's lots of further reading if you're interested in this kind of stuff. This original blog from 1994 is still relevant today. The PE format that's used on Windows hasn't changed. There's this guy Bruce Dawson who is publishing articles almost every week at the moment about particularly he works for Google, and he's really down deep with JavaScript engines and Chromium and memory usage and CPU usage, and why your 24 cores on your PC suddenly wait for a while, and how different locks behave and so on. Really great blog that he has. We actually have our own tech blogs, which you're very welcome to look at. I hope to publish something on there about this particular talk. And of course, we have a public GitHub, including our STL reference implementation. And you're welcome to follow me on Twitter or Tech at Bloomberg. And I really thank you for coming along, for your interest in this talk. I hope you found it somewhat useful. I'd be happy to answer any questions, but thank you so much.